Welcome everyone. I am Rati Ludhani, pursuing PhD at Department of Mathematics, IIT Bombay. I am a PMRF fellow here. Today we are going to discuss sample questions related to week 8, which is related to lecture 17 and 18. So let's begin. Feel free to ask any question. Just unmute yourself. Right. Consider the following ring R, which is equal to zx mod ideal generated by x square minus 1. Then which of the following statements is true? Okay, so ring is given to be zx, ring of integers here, and ideal is x square minus 1. Just take this quotient ring. Then what has been asked, whether R is an integral domain or R is a field or R is not an integral domain, none of the above. So let's see if that is an integral domain. So for integral domain, from the definition, what do we know? So for R is an integral domain. So it should be a ring first. So ring R is an integral domain. Sorry. If for all, if AB is equal to 0 for any AB in R, then either A is equal to 0 or B is equal to 0. So it is not possible that two non-zero elements of the ring multiply to give the value 0. So that is an integral domain. So let's see if that is happening in a ring or not. So okay, so any element of this R zx mod x square minus 1 will look like what? So here if you see, you have any element of this, that is some polynomial of degree n, and let's say we can write it as we always write. Okay, I'm using this kind of x, so let's stick to that only. So 0 to n, this mod x square minus 1. So we are dividing by this, so this is an ideal generated by this. So any element in so this ideal is actually what? R into x square minus 1, multiples of x square minus 1, where R belongs to zx. Okay, so here any polynomial mod this. So actually we can write, because if it is divisible, so we can actually write mod x square minus 1, just x square minus 1, that is also okay. Okay. Okay, I can use bar. Okay, this is something like that. So any element will look like a plus I. So any element of some just R mod I, okay, we are using R, so let's write J mod I. It is like any element A plus I where A belongs to J. So it is like that. So in that fashion we have this kind of notation where okay, or maybe we can write f plus x square minus 1, and where f belongs to zx. So we have written from the definition of zx, we can actually write n belongs to n, and that is okay, because a0 could be 0, so in that and a1 could be 0. So where ai is belongs to z for all I. Okay, so this is from the definition. Now what do we have? Now what is this element look like? So here I is equal to 0 to n ai x raised to power I plus x square minus 1. So whatever the multiple of x square minus 1 will can go in this ideal. So any element will look like of the form. Okay, so x square is equal to 1 here. So whenever we have x square, we can actually put it to be 1. So this is the ideal way to write if you want to. So so we have actually ax plus b, because whenever x square comes, we can write it to be plus 1. We can write it to be 1. Yeah, exactly. So this is actually of the form some a plus bx. Okay, and so because afterwards we have something, so x square will become 1, x cube will become x, because x square is 1, that means x cube is x. Okay, so just identify like this. Then we have so all the elements are of the kind this. Okay, such where a and b belongs to right z. So this set is actually, I can use scrolling vertical. Yeah, so zx, which is your zx mod x square minus 1, which is your r, is equal to the set a plus bx plus x square minus 1, ab belongs to z. For simplicity, we can actually write it to be a plus bx bar. Okay, so one more thing to note here, we cannot go beyond that. So we don't know what is x here, so x is like an remainder, because we are dividing by x square minus 1, so you will have some linear polynomial, not it is always possible to have some this kind of polynomial, so we cannot go beyond that. Now let's see, do we have some non-zero polynomial? If we multiply them, it lands in this ideal. So let's see, so that will check if it is an integral domain or not. So if you take so x square minus 1, so the ideal way to do that, just try to factorize in zx. If you are able to, then you can get it. So if you see here, x minus 1 into x plus 1 is equal to x square minus 1, and both of these polynomials belong to zx. So actually these exist in zx. So if you take x minus 1 bar and x plus 1 bar, then and you take the product is simply the multiplication from the quotient ring formula, like a plus I into b plus I is equal to ab plus I. So from this you have this, so this is x square minus 1 bar. And what is this? This so this is actually x square, or I could write 0 bar. So 0 bar means you have, so 0 bar means 0 plus ideal generated by x square minus 1. So it is like that. And if you see, this element is non-zero in this ring, and this is also non-zero in this ring, because because these are not the multiple of x square minus 1. So, and x minus 1 into x plus 1, sorry, not into, these both belongs to, not both, these are non-zero. Okay, non-zero in R, so R is not an integral domain. Okay, I hope this is clear. Okay, so first is definitely not true, and C is true, because R is not an integral domain. What about field? So this is a clear property that it's maybe you can say theorem if you want it, but it's very easy to see that any field is an integral domain. This is clear because of the fact that any field is an integral domain. Why? Because inverse exists. So multiplicative inverse exists. And you can easily check if that exists, then it has to be an integral domain. For every element of f star. So f star is f minus 0. So because of this, it is clear that this is not a field. If it is a field, then it has to be an integral domain. So only C option is correct. Okay. Let's move to the next question then. A message X is being sent via noisy channel such that at most C bits get corrupted in the transmission. So what is happening? You are sending a message. So there's a channel which is actually noisy. So here's a sender and maybe receiver. Okay, so it has been sent. Now the message is X, and at most C bits get corrupted in the transmission. So what is happening? You have some X as a your maybe whatever it is, like these are like bits. So you have something of this kind of message, and when you send, then it gets corrupted by C positions. So you don't know which are these positions. So any C positions got corrupted. Okay. Now to recover the original message, we send n copies of X concatenated together. So we now, but we want this message to be the original message, because we want to recover it. Okay, so now what is happening? We send n copies of X. So for example, you want to send 0 1. You have X to be like 0 1. Now you want to send it over this noisy channel, and for example C is equal to 1. So this has become what? For example, C is equal to 1. So for example, this becomes 1 and 1. So this got corrupted, but we don't know that. We have just this message. So we have just this message. So this has been received. Okay, what is this? Yeah. So this has been received. Now so how can we get the original message? So what we are trying to do? So these are called repetition code actually. So what we are trying to do, we are just repeating repeating X n times. So for example, let's see 0 1 0 1 0 1. It's like that. So this has been repeated 3 times. So let's see, if we repeat 2 times, what will happen? We still know that one position has been corrupted. So one position is being corrupted. So now the message you received is like, so what at any place it could happen. Now you have received this. Now since you know that it has been repeated 2 times, that means the position, for example, this 1 and 0 should be same, and okay, it could be in, oh, that's okay. So 1 and 0 should be same, and 1 and 1 this, so these are 4 places. So this place and this place should be same, and this place and this place should be same. So here if you see 1 and 1 is same, but here 1 and 0 is not same. So you know that there is an issue. So there has been some corruption here, but you don't know what is that, because 1 and 0, it could be anyone could be the correct one. So 1 or 0, anyone could be the correct one, but you know the other one is 1, but you don't know what is this message. So now if we repeat just 2 times, we cannot get the correct value. So we don't need to just detect it, we need to correct it also. So it has been asked if it is correct or not, the corrected message we want. But if it has been asked that if you just be able to detect it, then that is okay. So let's see, for correction what you need to do. You repeat it again, like 3 times. Take it 3 times. Still you know the C is equal to 1. Only the one position has been corrupted. So what will happen again? I'm just doing it with the same position just to make it clear. Now you know what is happening here. So this message has been repeated 3 times. Now you know only one position has been corrupted. So clearly this one is same, so you have this one. For the first position, what is happening? Here you have 1, here you have 0, and here you have 0. So you know that one position is being corrupted. So that means 2 positions cannot be corrupted. It cannot be possible that 1 became 0 at these places. So it must be, you just take the maximum value. So you take the value which is constant for maximum points. Okay, so maximum position, so that is 0, and here 0, the frequency of 0 is 2 times and frequency of 1 is just 1 time, so it should be 0. Okay, so if you observe what is happening in this case, so whenever if you want to detect it, you should be able to find the maximum value. Okay, so frequency in this maximum value sense. So in that case, if you have C, whatever here you have C is equal to 1, but if you have C is equal to 2, then what should happen? So 2 places could get corrupted. So what should happen? You should be able to have maximum value. So now in that case, what should happen? C is equal to 2. So it should be 5 values to 5 time repetition, so that you can get the value, because you need 2 corrupted positions and 3 should be correct positions. 3 positions which is from the original one. So if you need that, you need and 2 is corrupted one. So you need at least 3 more than so what is happening? So more than this 2, so that means just 2 plus 1, just take 2 plus 1. So what is happening? 2 you have, and this 3. So if you want to write, you want it to be, and what is 2? What is 2 here? That is C. And here what is this? You want 1 extra from the cardinality of this corrupted positions. So that is C plus 1. So what should happen? So 2C plus 1 times you should repeat at least. Okay, at least you need that to have the correct thing. So here what is happening? To recover the original message, we send n copies of X concatenated together. So you just take like 0 1 0 and just take the join, such that error correction can be done. Correction can be done. It is not asking for detection. So these are 2 different questions if you observe. So such that error correction can be done at the receiver end correctly. So what n should be chosen? So n should be chosen in a way that it is minimal. So that this is the minimal n which we need in our thing. So choose the correct option. So if c is equal to 3, n is equal to 6, let's check. So it should be 2 into 3 plus 1, that is 7. So n should be 7, so that is not true. N is equal to 2c, again no, because 2c plus 1 is required. 2c could create a problem like this. For any c, n is equal to 2c plus 1. Clearly this is true, as we have proved. Both a and b are true. No, not possible. So also if they have asked for the minimality, if you choose 2c plus 2, that is big enough. So you can have 2c plus 1. So if one of the option is 2c plus 2, that is wrong. Okay, I hope this is clear. Let's move to the next question. Let G be a cyclic group of order n with generator G. So G is given to be a cyclic group generated by G and order of G. So it is generated by G and cardinality of G is equal to n. So that means order of G is clearly n. This implies G raised to power n is equal to identity and G raised to power not n, let's say G raised to power I, maybe let's say S is not equal to identity for all S bigger than or equal to 1 and not equal to n. Okay, so order of G is equal to n. Now it has been asked what is the order of G raised to power m, and m is general, so clearly m is asked, m is given to be m is greater than or equal to 1. That is the obvious choice, obvious thing it should be. So I'll keep it in the question itself just for clarity. Okay, yeah. So now order of G raised to power m is being asked. Now let's see what is happening. So this implies, so let order of G raised to power m is equal to I. This implies what? G raised to power m raised to power I should be identity and I should be minimal and also I is greater than or equal to 1, because if you put I equals to 0, then definitely it is identity. But first thing, I is greater than or equal to 1 is from the definition, because order should be positive integer, should be minimum in the sense, what does that mean? If you take that is G raised to power m j, if you take it is not equal to identity for all j in between, not equal to, right? Okay, so let's see what is happening here. So this is the case, G raised to power m raised to power I. This implies what? G raised to power mi is equal to identity. You know one thing from here, G raised to power n is equal to identity. So what should happen? And G raised to power n is equal to identity, or maybe I'll write, that is confusing maybe. This is minimal, so, and this is true. And now since G raised to power mi is equal to n is equal to identity, this implies, so what should happen? So this implies what? Mi should be 0 mod n. So what does that mean? Okay, I'll write it. That is mi should divide n, or the other way around, n should divide mi. So since you know G raised to power n is equal to I and n is the minimal in that sense, so mi, where n is minimal, Okay, so n is minimal in that sense, so n should divide mi, right? Mi and like mi should be equal to 0 mod n. For example, mi could be 2n depending on the values, or 3n or something. It should divide n, n should divide mi. So what does that mean? This implies mi is the least, because I is itself least, I is minimal according as per the above things. Mi is the least positive integer such that m divides mi, and so this is pretty clear, or maybe that's why I'll write n divides mi, and clearly m divides mi. Okay, which is not required to be written because it is written in the form of mi. Now this is happening, and this is least positive integer, so this implies mi should be LCM of m and n, least common multiple of m and n, right? So that is from the definition. So since we know that GCD of m and n and LCM of m and n is equal to m into n, so this is very standard result. So GCD of m and n, so what does that mean? You can find out the value of LCM. So what is LCM? LCM m into n is equal to mn by GCD of mn. So if you compare with these and this implies I should be what? I should be this value. I should be n by GCD of m and n. So let's see if we have such an option. Right, so n by GCD of m and n. So that is your correct answer, right? Also, if you want to check for the other options, do we have examples for the if they are not correct or not correct? So okay, they are saying order of g raised to power m should be n. So for example, take take z4 under addition. So what do we have? You have 0, 1, 2 and 3. So 2 is of order 2. If you see, so 1 square is what? 1 plus 1, that is 2, right? So 2 and if you take 2 plus 2, you get 4, that is 0. So that means the order of 2. So if you take 1 square, so if you take if you take m is equal to 2 and g is equal to 1, then you have 2 raised to power 1 raised to power 2 is equal to identity, that is 0, and that will make it like you have the order to be 2, and here it has been asked n, so that is not true because n is 4. Now for LCM and LCM of n and m, so it is clear, the same example you can take. N is 4, m is 2, so LCM is 4, again it is not true. Equal to order of g, again that is not true. This example fits for everything. Okay, so that is clear, I hope. Okay, let's move to the next question then. Okay, let GL2, you have this group A where A is a 2 cross 2 matrix with with entries in F2, and determinant of A is equal to 1. Then what is the order of GL to F2? Okay, so order has been asked, that is the cardinality of this set. So they have asked GL to F2, the cardinality of this set. Okay, so let's see if we can figure it out. So this is a very standard group, general linear group. Actually, from the definition, it is always without determinant, that is a special linear group, but let's say whatever is given, it's fine. So it's like a definition here. So determinant of a is equal to 1. Actually, that's okay, because in this case, okay, I'll write it for the information. So this is, I'm writing in general F. A is n cross n matrix with entries in F. So this is a field, okay, with entries in F, and determinant of A is non-zero. So that is actually the definition of general linear group. And when you say special linear group, this is A belongs to GL and F with determinant of A is equal to 1. Okay, this is the actual definition. These are the definition, standard notations. But if you see here, here the field is given to be F2. So so determinant is what? Determinant is the multiplication and addition of the elements in F. That is again an element of F, because field is closed under addition, multiplication, and even this minus sign, so you have subtraction, so additive inverse also. So that element will belong, determinant will also belong to the field. So because of this, determinant of any matrix A should be in F itself. Now field is given to be F2. That means you have just two elements, that is like Z2. So you have just two elements, 0 and 1. So that is field. So that is like two elements, 0 and 1. Okay. So what are the options now? So determinant cannot be 0. So the only option is just determinant of A is equal to 1. So it is, this is actually equal to SL2 F2. These are the same thing here. That's why it's fine to write it. Just explaining the notation. So that's fine to write it. For example, if it is given F3, then determinant could be 2 or 3. Determinant could be 1 or 2. Both are the options. So in that case, there's an issue. So in that case, these two things are different. Okay. So let's see. Now we need the values. Okay. So any element of this GL to F2, let A, B, C and D belongs to GL to F2. So that means this implies A, B, C and D belong to the set F2, that is 0 and 1. So it either this is 0 or 1. This is like Z2, so it's like 0 mod 2 and 1 mod 2. You can use bar. So yeah, you have this. Now so if you want to write the operation, it is like 0 plus 0 is equal to 0, 0 plus 1 is 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 0. It's like 2. So it's just like Z2 with the plus mod 2 minus mod, not minus, multiplication. Okay, so it is like that. Now ABCD should belong to these values, and AD minus BC, which is the determinant, so I can write it, and determinant of, let's call it A, determinant of A is equal to AD minus BC. It should be non-zero. Non-zero means just 1 in this scenario. So what are the options for ABCD that we need to find out? So This implies now all these elements belong to 0 or 1 and you have this thing. So what are all the possibilities? So to make it easy, actually I can write it AD is equal to 1 plus BC. Now see what are the options. So let's say A and D is equal to 1. Now if this is true, if this is equal, A and D are 1, so multiplication will again be 1. So this we have 1. At this position it should be 0. So this means if both of these are 1, then there is an issue. So either B is equal to 0 or C is equal to 0. One of them has to be 0 at least. Could be possible that both of them are 0. And what is the other option? If this value is 0, that means either A is equal to 0 or D is equal to 0. And if this is 0, this multiplication is 0, this part should be 0 too. So that means BC should be 1. So that means B is equal to C is equal to 1. That is the only possibility. Now check in this condition. In this condition, what are all the possibilities? Like B is equal to 0, B is equal to 0 and C is equal to 1, B is equal to 1 and C is equal to 0, and B is equal to 0 and C is equal to 0. These are three possibilities here. What does that mean? This means you have three options for this thing. So you have three choices, plus for this is the same kind of thing. So you have three choices again. So this implies you have 6 options for AB. For the tuple, for example, for the matrix ABCD, you have 6 options. So this implies cardinality of GL2F2 is 6. Let's see. Yeah, we have this option correct. Okay, great. Let's move to the next question. Consider the quotient ring Z mod 14 into 21. So you have the ring, quotient ring Z mod 14, 21. Consider the following statements. So, okay, again, what is that ring? Let's understand what is this ring. Z mod, so this implies, so firstly understand what is this ideal. And if you know the ideals, this Z is a principal ideal domain. If you know, if you remember, you can actually prove that. We have proved in the last lecture, I guess. Last to last, just check it. So Z is a PID, so it should be possible that there is one generator for this, and if you remember, that is GCD of M and N. So if it is generated by M and N, that is equal to GCD of M and N, if I'm not wrong, right? So that is equal to 7. What is the GCD of 14 and 21? That is 7. And you can actually figure it out from the definition itself. What is this? This is 14 M1 plus 21 M2. And M1 and M2 belongs to Z. Right? So what can you get? Now here if you see 7, you can take it out. So basically you need to find out what is the least element from this. So that is your GCD, or you may take 7 into 2M1 plus 3M2, where M1 and M2 are all possible integers. Now this is what? This could be 1 because 2 and 3 have GCD 1. So that means there exist M1 and M2 such that this value is equal to 1. This implies you have 7 in this set definitely. So 7 you have, and you could have the from this set you can say that you have 1, and if you have 1 you can have all the multiplication to that. So that means this is just N belongs to Z. So this is actually multiple of 7. Okay, so you have this. So that means you are actually talking about Z mod this. So that Z mod 7Z, that means, and that is, if you know, that is just Z7, because what you are doing, you are just erasing all the multiples of 7. So that means you can actually identify it as 0 bar, 1 bar, 2 bar, 3 bar, or you want to write, and 6 bar. This is your set. Now let's see what they have asked. Z mod 14, 14, 21 is a field. So Z7 is a field, so we are done. Z7 is a field, so that this is definitely true. So S1 is true. What about S2? Z mod 14, 21 is 14 elements. So definitely this is not true. This is false, because because Z7, which is actually maybe isomorphic to Z mod 14, 21, has 7 elements. Cool. Okay, so this is false. So which option is correct? S1 is true, but S2 is false. So C option is correct. Very good. Okay, then let's move to the next question then. For ring R and S, ring homomorphism is a function. So this is, so it has been defined what is ring homomorphism. So you have some, so this is a ring homomorphism. If what will happen? If it is additive, that means if you take R1 and R2 from R, then it should be equal to this for all R1, R2 belongs to R. Second, multiplicative. That means if you take R1 and R2, multiply it, then these are equal for all R1 and R2 belongs to R. What about third? And unity preserving. So you have unity preserving, that means identity of R should map to identity of S. So this is not something which is always, so I should say this is not something which we enforce in a ring homomorphism, but here it is given that this satisfies unity, this satisfies this property, like this preserves unity. Okay, if this is the ring homomorphism, then in which of the following pairs a non-trivial ring homomorphism is possible? So non-trivial, they said, okay, they should not say because 0, so usually non-trivial is for 0 map, okay, or maybe if these sets are equal, then we can say the identity map. Okay, so here it is non-trivial, means it is not mapping it to 0, and actually which is not possible because it is given that 1R goes to 1S. So identity of R goes to identity of S. So let's see if that is a possibility. First thing, Z10 to Z11. So this is your map, R is given. So let's see if properties are, so 1 of Z10 should map to 1 of Z11. Okay, so that is mod 11, and this is 1 mod 10. So if this maps, then what will happen? So these are like, so this property should hold. That means what? 1 plus 1, F1 plus 1 should map to F1 plus F1. That means 2 bar should map to 2 bar. Similarly, if you go here, if you see 10 bar is what? 10 bar is equal to 0. So 0 should map to what? here where it is mapping, it should be 10 bar, and that is as it is. So 10 bar is not something 0. So if you check from the properties, if you take R1 and R2 to be 0, then it is clear that F0 should map to 0. So this sole property implies F0 should map to F0. So 10 bar is not equal to 0 clearly, because this is not equal to 0 mod 11. So that means here what is happening, 0 bar is mapping to 10 bar, which is a problem, right? So it should not happen, and so this is not possible. So any non-trivial ring homomorphism is not possible in this case. Okay, what about second? F is the map from F12 to F22. Okay, so here again let's see, here 1 mod 12 should map to 1 mod 1 mod 22. So this implies 2 bar. So if I am writing this side, that means 2 bar means 2 mod 12, and if I am writing this side, that means 2 mod 22. So this is 2 bar, and similarly if you go, so clearly you see that this is less value, so that should create a problem. Oh, 1 second, this is a ring homomorphism. So right, no, that's okay. Yeah, inverse need not exist, so F22 is normal, which you're saying. Okay, so if you take it to 12 bar is equal to 0 bar here, and it should map to 12 bar of this 12 mod 22, and this is coming from simply this property. You are just doing F1 plus 1 for F2 plus 1, it's like this, you are doing this only. Okay, so this is mapping to 12 bar, which is not equal to, clearly not equal to 0 mod 22. So this is again creating a problem. So this is again not a ring homomorphism, and so you cannot have any ring homomorphism in this case. What about third? Z36 to Z18. So actually if okay, let me tell you what is happening, when it will be and when it will not be. So from these observation, it is clear, if this number, if the domain is less, like if this number in Zn, so if you have Zm to Zn, then m must be greater than or equal to n, first thing, because if it is less, there is a problem. So must be this. And now there could be a problem again. So in this case, let's see. Okay, so 1 bar is going to 1 bar, that is mod 36 and mod 18. So if you take 1 bar goes to 1 bar, then what will, this has to be, so 1 bar is going to 1 bar, then 2 bar will go to 2 bar, and if you go till 36, now see, so 0 bar okay, so actually I am saying this is a perfect ring homomorphism. Why? Here if you see, if you reach at 18, then it will go to 18 bar, which is 0 here. So that's quite okay. It could be like many one function. So it is like 0 bar is mapping to 0 bar, no doubt. So that's okay. So as you go until 36, if you reach at 36, that is 0. It should be 0 here also. So it for it to be 0, so 36 bar is what? 36 mod 18, and 36 is a 18 to the 36, so it is a multiple of 18, so this should be 0. So this is 0 bar, so 0 bar is mapping to 0 bar. So at this stage also, what should happen, whatever number you have m, so this n should divide m. So this should also be a condition, because if it will not happen here at this step, there will be a problem. It should be a multiple of 18. So these two conditions are required. So yeah, so I can highlight it. So this is something which is a requirement in your case to have a ring homomorphism. So F is a ring homomorphism. Ring homomorphism, something short. If F from this to this is a ring homomorphism, if this and this, okay. Actually, you can just write n should divide m. So it clearly means n is less than m in integers, definitely. Okay, so from the question, this option is correct, and definitely not both A and B. Okay, so I'm done with my questions now.